Hello, my name is Frédéric Pouillot, and I'm the director of the Clean Energy Institute, the education division of GPEX. GPEX is a company specialized in clean energy project due diligence for various renewable and clean energy technologies dealing with the production of power, heat, cooling, and transportation. In partnership with Leonardo Energy, we are offering these multimedia slides as part of a series of courses on feasibility analysis with RETScreen. In this presentation, which will last a little less than 1 hour, we'll provide some relevant background information useful for anyone who wants to evaluate a solar photovoltaic project using tools such as RETScreen. Please note that this material is complemented by other videos that will guide course participants step by step through case studies of PV project analyzed with RETScreen. Also, our courses will provide a number of guided, relevant case studies as well as exams that can lead to course completion certificate or proficiency certification. In this video, we'll start by explaining applications for solar PV. We'll review the main components of PV systems, such as what people call panels, and various electronic and other components. We'll discuss central versus isolated grid, benefits as well as limitations of various PV integration approaches. We'll then cover economical aspects and specific configuration options for off-grid systems. Special attention will be given to benefits and applications for water pumping systems that are driven by solar PV. We will then examine what resource can be expected based on location, season of use, and how the resource can be best captured using devices that follow the sun path. The next slide will explain that based on PV system use, various types of seasonal or diurnal solar correlation may impact the design of PV systems. Since one of the main goals of RETScreen analysis is to find out the economics of PV systems, we will of course discuss PV system and energy costs. Besides energy and equipment cost, there are many considerations that may affect the viability of a PV project, and we will introduce some of the traditional considerations. The next series of slides will provide illustrations of applications for solar PV in various parts of the world. Finally, we'll introduce a RETScreen PV model and explain what is covered by the tool. The logical path of how the model makes energy calculations will be shown. We'll explain why RETScreen's accuracy is appropriate for financial due diligence. In conclusion, we'll summarize the benefits of RETScreen for due diligence on solar PV projects.
This is the Photovoltaic Energy Project Analysis module of the RETScreen Clean Energy Project Analysis course. Here we discuss the operation and application of photovoltaic energy systems, such as the one located on the roof of this research laboratory in Varennes, Quebec, Canada. Let's start by answering the question, what do photovoltaic, or PV, systems provide? Photovoltaic systems provide electricity. A photovoltaic module, such as the blue panel being mounted on the roof in these photos, generates a small current when sunlight strikes it. This current can be used to power isolated loads or can be fed onto a grid, an interconnected web of generating stations and transmission facilities that provides electric power to a number of distributed consumers. In other words, PV can provide electricity to devices as small and simple as handheld calculators, or to networks as large and complex as the power system that brings electricity to most homes in North America. While photovoltaic modules generate direct current, or DC power, a photovoltaic system will often include components that convert this into the alternating current, or AC power, that is required by many common appliances. PV systems that are not connected to the grid will also typically include battery storage, permitting the system to provide power at night and during cloudy periods. Photovoltaics can also provide power for water pumping, In many places, water needs to be pumped from wells or sloughs as a source of drinking water for people or livestock. If the electricity grid is not nearby, photovoltaics can cost-effectively generate electricity for a water pump. While an electric water pump is not fundamentally different from other loads, such as lights and radios, photovoltaic water pumping is usually treated as a separate class of PV system, mainly because the ultimate quantity of interest is water, not electricity. Photovoltaic systems have a number of attributes that are as important to some people as their ability to generate electricity or pump water. These attributes are all illustrated in these photographs of a photovoltaic installation on a home in a part of West Bengal, India, that is not served by the electric grid. First, reliability. Photovoltaic modules are one of the most reliable sources of electricity ever developed. They contain no moving parts and will function without human intervention for decades. This is crucial in locations, such as West Bengal, where the expertise and infrastructure needed to maintain complex power systems is not available at a price the system owner is able to afford. Such locations are not found only in developing countries. They exist around the world and even in outer space. Satellites and space probes were the original motivation for the development of photovoltaic technology. Second, simplicity. PV systems contain few components and have very basic operating and maintenance procedures. This makes them well suited to the people in this village, who probably lack the training and familiarity necessary to operate a fossil fuel power generator. Third, modularity. The power that a photovoltaic system provides under given conditions of sunshine is largely dictated by the size and number of photovoltaic modules in the system. Add more modules, and the system provides more power. This makes it easy to scale the size of the system in response to changes in the demand for electricity or the availability of capital. For example, if the household shown here plans to buy a television in 5 years' time, they will be able to upgrade their power system when the additional demand arrives, and not be forced to find money now to pay for an unnecessarily large system. Fourth, image. Few power systems captivate the imagination like photovoltaics. Its image is high-tech and green in the developed world, and in the developing world PV may be a token of modernity that diminishes the lure of the big city. Fifth, and finally, silence. Generating electricity in utter silence, a photovoltaic system is a godsend to those many people who would otherwise have to live or work near a diesel or gasoline-fired generator. Components of photovoltaic systems. While the building block of a photovoltaic system is the photovoltaic module, modules themselves are composed of photovoltaic cells. These are thin, flat sheets or strips of semiconductor that are sensitive to light. They convert a portion of the light's energy directly into electricity. The semiconductor most commonly found in photovoltaic cells is silicon, a plentiful element found in sand. Under bright sunlight, a typical photovoltaic cell measuring 10 centimeters by 10 centimeters will generate about 3 amps of current at 0.5 volts, or about 1.5 watts. This is a small amount of power. If 30 or so of these cells are connected in series, the output will be around 3 amps at 15 volts, or almost 50 watts, which is enough to power small loads. Such an assembly of cells, encapsulated in a weatherproof envelope of glass and plastic, compose a photovoltaic module. When a single photovoltaic module is insufficient to supply the desired quantity of power, it can be wired into an array consisting of multiple modules. The array is mounted on a structure that orients it in such a way that it will catch a reasonable amount of sunlight. For example, this structure may be a tilted roof that, in the northern hemisphere, faces south. Because a photovoltaic module provides little electricity during overcast periods and no power at night, off-grid photovoltaic systems generally must store excess power generated during sunny periods. A battery or, in water pumping systems, a reservoir, fulfill this function. About 90% of the batteries used in photovoltaic systems are of the lead-acid variety. While the lead-acid battery is relatively cheap and common, it is not as long-lived as the photovoltaic module and requires some maintenance, such as the replenishment of water lost during use. Photovoltaic systems may also include electronic power conditioners. These manipulate the output of the array such that it matches the current and voltage requirements of the load. Inverters are common power conditioning devices that convert direct current into alternating current. With an inverter, the PV system can operate common appliances designed for grid power, such as standard washing machines and televisions, or feed its power onto the grid itself. Charge controllers, another class of power conditioners, limit the output of the array when it is charging a battery and the battery is full. Rectifiers perform the opposite operation to inverters. They convert AC to DC. This allows the DC loads and battery of a photovoltaic system to get additional power from an AC source, such as the grid or a rotating generator. A DC-DC converter permits the array and the load to operate at different voltages. This can be used to ensure that the array is operated at the voltage that generates the maximum amount of power, or to boost the current available to a motor or pump that is just starting up. A photovoltaic array need not be the only power source in a PV system. A diesel, propane, or gasoline-fueled generator, or genset, can furnish power when loads are especially high or there is little sunshine. At mid-latitude locations, winds are often strongest during the winter, precisely when sunshine is weakest. Thus, wind turbines and photovoltaics can complement each other. Whenever two or more generating sources are combined, a so-called hybrid system results.
Apart from the basic components reviewed in the previous slide, the balance of system, or BOS, includes other important elements. Support structures, or racks, need to be used to fasten the array modules either to a building or to the ground. The simplest type of PV array support structures are fixed structures. These can be installed either using a ballast system or structural attachment. Ballast systems are often preferred for their low cost in lower latitudes on flat surfaces. Structural mounting are systems that attach to buildings or to the ground using perforations or foundations. These systems are typical on residential roofs or slanted roofs, or when a flat roof cannot accommodate the extra weight of ballast. Tracking systems use single or double axis trackers. They are required for concentrating PV technologies and may be preferred for other reasons. In some contexts, they allow utility scale projects to reach a lower levelized cost of energy. They may also be a better option in high latitudes areas where open and cheap space available. Ground systems may use special types of foundations. An interesting type of foundation is the screw approach that is fast and does not require concrete. PV arrays need to be connected to other components, the load or the grid, through cables. The type of cable depends on various factors such as AC versus DC, size of system, and distance between PV production and its use of grid connection. On-grid systems also require meters that are used to measure the kilowatt-hour sold or purchased from the grid. Large PV plants or farms may require, in addition to inverters, step-up transformers or dedicated buildings to accommodate them. The connection between the PV production and the point of use or the grid may require digging trenches and adding utility poles. Finally, especially with large systems, special fences and security systems are typically put in place to prevent panel theft. Large PV plants typically also use elaborate remote monitoring and control systems that can be used both for security but also to optimize the operations and maintenance.
On-grid systems. Let's divide photovoltaic systems into three distinct classes: on-grid, off-grid, and water pumping, and examine each of these in turn. The grid, as mentioned in a previous slide, is a collection of geographically dispersed consumers and generators, all interconnected by electrical transmission and distribution lines. A photovoltaic array can be one of a large number of generators providing power to a grid. Photovoltaics can be integrated into the grid at a central plant or distributed around many locations on the grid. The centralized approach is familiar to the utilities accustomed to conventional coal, hydro, gas, and nuclear power plants. In general, this approach facilitates system control, operation, and maintenance and leads to economies of scale. It is questionable whether these advantages are significant for photovoltaic systems, however, due to photovoltaic's inherent modularity, simplicity, and reliability. The distributed approach, though inappropriate for conventional power plants, is applicable to photovoltaic systems. In its favor, it overcomes a major disadvantage of centralized integration, in that distributed systems can be mounted on roofs and facades, whereas the cost of a large tract of land for a central PV array can be very significant. In distributed integration, the PV array will typically be located on a building. When the sun shines, the PV-generated electricity will power some or all of the loads in the building. This reduces the amount of electricity that the building owner must purchase from the grid. Should the output of the array exceed the total load of the building, it is technically possible to sell electricity back to the grid. Many utilities, though not all, permit this. Photovoltaics can be integrated into either a central grid or an isolated grid. A central grid is one that covers a vast geographical area with thousands of generators and millions of consumers. The North American electricity grid is one example. An isolated grid is a smaller network of generation and distribution facilities not interconnected with the central grid that supplies electricity to a limited area, such as a single remote community or the communities on an island. While there are a large number of on-grid photovoltaic systems installed around the world, such systems are rarely competitive with conventional power plants, at least on a cost basis, except when the PV system is in some way subsidized. Off-grid systems. Now let's turn to the second class of PV system, which supplies power to a load that is not connected to any grid. Many small off-grid loads can be powered by a standalone PV system. These systems may involve nothing more than a photovoltaic module connected to a battery and the load, though most will also include a charge controller. They are extremely reliable since there are so few components, no moving parts, and minimal electronics. At higher latitudes, there will be less sunshine available during winter, and an array able to provide power to a large load over the winter may be very costly. The larger the load and the more pronounced the difference between the availability of sunshine in summer and winter, the better the case for adding a fossil fuel powered generator or a wind turbine to make a hybrid system. Unlike on-grid systems, off-grid systems are often very cost-effective compared to other power sources. This is especially true when loads are small, perhaps 10 kilowatts or less. Extending the grid to an off-grid load has extremely high capital costs, even compared to the high capital costs of PV systems. Small loads cannot justify the practically limitless power available from the grid. Providing power solely with a genset or by non-rechargeable batteries is initially inexpensive, but burdens the operator with high, ongoing fuel or battery replacement expenditures, frequent site visits, and genset maintenance and overhaul. In the long run, these costs mount and make the more capital-intensive PV system attractive. Water pumping systems. This, the third class of PV system, is a special type of off-grid system. Its two distinguishing characteristics are that there is usually just one load, the water pump, and that a reservoir generally supplants the battery. Different types of pumps are suited to different conditions of desired flow rate and head, or vertical distance that the water must be lifted. For head below 6 or 7 meters, suction pumps, which draw water upwards by creating a negative pressure, can be used. These pumps need priming, that is, they need to be filled with water before they can operate. For higher heads, centrifugal or volumetric pumps must be used. Both of these types of pumps must be located on or in the water source. Centrifugal pumps impart momentum to the water by flinging it out the vanes of a spinning rotor, thus pressurizing the flow. They work well when large volumes of water are required, but are sensitive to variations in the head. For high or varying heads, especially when modest flows are required, volumetric pumps can be used. These draw water into a chamber, close the inlet, and then force the water up and out of the chamber. Then the outlet is closed and the cycle is repeated. When the head is high and large flow rates are necessary, a multi-stage centrifugal pump, which draws the water through a series of rotors one after the other, is required.
The power conditioner is an important part of many pumping systems. Depending on whether a DC or AC motor is used in the pump, the conditioner may be a DC-DC converter or an inverter. The power conditioner helps the photovoltaic array provide the high current that may be needed to start the pump, even under low sunlight conditions, and operates the array at a voltage that generates maximum power, regardless of the operating voltage of the pump motor. A battery can fix the voltage and provide starting current, thereby replacing a DC-DC converter, but this introduces complexity, maintenance, and inefficiency.
Like many off-grid applications of photovoltaics, water pumping can be very cost-effective. In the developed world, it is used when water for livestock must be drawn from a well or slough that is remote from the electric grid. It can also be used for domestic water supply for an off-grid home. In the developing world, its typical application is the provision of water for a village. Solar resource. Compared with other energy sources, sunshine is fairly dilute. One must have a large array to collect significant amounts of power. On the other hand, the solar resource is more evenly dispersed over the globe than most other renewable energy resources, such as wind and hydro. That is, there is a modest solar resource available everywhere, at least considered on an annual basis. Let's examine what this means for photovoltaic systems. First, we need to introduce a bit of terminology. The capacity of a photovoltaic array is rated in terms of its power output under standard test conditions of bright sunshine and cool temperatures. The unit of capacity is the peak watt, which is written as a capital W with a subscript P. A 100 peak watt array, for example, will furnish about 100 watts of power if squarely oriented towards the sun at noon on a cool, clear spring day. When there is less sunshine, the array provides less power, but is still called a 100 peak watt array. At the vast majority of locations on the planet, a peak watt of installed photovoltaic capacity oriented to catch the sun will generate between 800 and 2,000 watt-hours of energy per year. The low end of this scale corresponds to a cloudy, high-latitude site, such as found along the northern coast of Norway. The upper end of this scale is representative of Botswana or other particularly sunny countries in Africa. It is possible to find sites that fall outside this range, for example, on mountain ridges normally in cloud, but they are rare. While the annual solar resource is relatively similar for most locations the world over, the difference between the sunshine available in winter and summer becomes more pronounced at points near the poles. This is especially problematic for off-grid systems that must operate year-round. To increase the winter output of a fixed array, its tilt angle measured with respect to the horizontal should be increased. An angle equal to the latitude of the site plus 15 degrees is often used. For comparison, to generate maximum output over the year, a tilt angle equal to or somewhat less than the latitude should be employed. A more vertical array catches more sun during the winter, when the sun is low in the sky. Increasing the tilt angle makes only a limited improvement to the wintertime performance, unfortunately, and winter loads at high latitudes may necessitate a hybrid system with a genset. Some arrays are mounted on racks that move throughout the day to keep the array oriented towards the sun. So-called trackers can increase the output of the array by 20 to 50%. They are only effective, however, for direct sunlight, not diffuse light on cloudy days. They do almost nothing to increase the winter output of arrays at high latitudes, since the sun's arc across the sky is very limited during this season. Furthermore, they add moving parts and complexity to the photovoltaic system. Trackers may be cost-effective for high summertime loads or on-grid applications, where only the total solar energy collected over the entire year is important. Solar load correlation. Solar energy varies on a seasonal basis as well as on a daily or diurnal cycle. When sunny periods coincide with higher than average loads, in cloudy periods with low or no load, an off-grid photovoltaic system requires less battery storage and operates more efficiently. When planning an off-grid system, therefore, the solar load correlation should be examined. Some typical photovoltaic applications have a good solar load correlation on a seasonal basis. Two notable examples are cottages and irrigation. Both are used during the summer, when the solar resource is good, and require little or no power during the winter. Diurnal solar load correlation can be positive, negative, or zero. Positive correlation occurs when power does not need to be stored in a battery in order to meet the load. This photo of a photovoltaic water pumping system shows one example. Nighttime loads, such as lights, exhibit negative solar load correlation. Zero solar load correlation arises when a load requires the same amount of power, on average, regardless of whether or not it is sunny. A telecom or monitoring station may be an example of this. Examples of PV system costs. Photovoltaic system costs vary greatly depending on location and application. To convey a sense of their costs, this slide compares two very different systems. The first is an on-grid home in California, USA. It has a 1 kilowatt roof-mounted array connected to the grid by an inverter. For this system, the purchase of the array accounts for about 60% of the total cost of installing and operating the system over its entire lifetime. The inverter is responsible for about 15% of the life cycle cost, and installation another 10%. The second example is a remote 2.5 kilowatt PV hybrid system powering telecommunications equipment in southern Argentina. Here the largest single expense over the life of the system is the purchase of batteries every 5 or so years. Fuel purchases for the genset are the second most important cost. Purchasing, maintaining, and overhauling the genset together make up the third most significant cost, mainly because the system is remote and maintenance visits require expensive travel by highly trained personnel. For similar reasons, design and installation of the system at this remote site is expensive. To summarize, battery and genset fuel and maintenance expenses dominate costs for the remote off-grid system, while the on-grid house is characterized by high initial costs and minimal long-run expenditures. The two systems are also very different in terms of their performance and cost effectiveness. In sunny California, the grid-tied house generates about 1.6 megawatt hours per year, whereas the PV array of the higher latitude hybrid system generates only 2.5 megawatt hours per year, despite being 2.5 times larger than the array on the house. The cost of generating electricity is an expensive 35 cents per kilowatt hour for the California house and an astronomical $2.70 per kilowatt hour for the hybrid system. But note, with grid electricity costing 8 cents per kilowatt hour in California, the on-grid photovoltaic system is not cost-effective. In contrast, the Argentinian off-grid system is far less expensive on a life cycle basis than the next cheapest power supply option of a genset battery cycle charging system, which generates electricity at about $4 per kilowatt hour. This illustrates the point that while photovoltaic systems can be expensive, for off-grid applications they may be cheaper than all other alternatives. Photovoltaic project considerations. A number of factors should be considered when developing a photovoltaic project. As pointed out in previous slides, photovoltaics are cost-effective off-grid but uncompetitive on-grid. Thus, the cost-effectiveness of photovoltaics at an off-grid site may hinge on an evaluation of the barriers to extending the grid to the site. If the load is small and the grid far away, such as is the case for this telecommunications site in a remote area of northern Canada, PV will likely be far more cost-effective than grid extension. If the grid is near, within a few kilometers, and the load large, more than a few kilowatts for example, photovoltaics will have more difficulty competing with grid extension. When sites are remote or difficult to access, the cost of visiting the site to bring in fuel or perform operation and maintenance tends to be high. This makes genset and primary battery systems less attractive than photovoltaic systems, which require less maintenance and benefit from automatic delivery of free fuel whenever the sun is shining. Photovoltaic systems have high initial costs and low operating expenses. In contrast, many competing power sources, such as gensets, are initially inexpensive but have high ongoing costs. It is critical, therefore, that operation and maintenance costs, and not just initial capital costs, be included in any comparison of different power systems. While PV systems rarely break, they may fail to provide power if there is a longer than normal period of especially overcast weather. Larger arrays and batteries decrease the risk of such failure, but raise the cost of the system. This results in an inherent trade-off between cost and reliability. During planning stages, the required level of reliability should be determined. A telecom system such as the one in this photo will demand very high reliability and be costly as a result. When an off-grid photovoltaic system is to provide power to homes, cottages, or villages, it is essential that the system's users have realistic expectations about what the system can provide. Furthermore, when photovoltaic systems are proposed for developing areas, the social impacts of the system should be anticipated. Lastly, intangible benefits of the photovoltaic system are often more important than costs. The high-tech image of the technology, its environmental benefits, its minimal noise and visual pollution compared to gensets and electric lines, and its modularity and simplicity may make it the power system of choice even when cheaper options exist.
Solar light and home PV systems. Examples from Tibet, Botswana, Swaziland, and Kenya. About 2 billion people around the world are not served by any electrical system. Most live in developing countries, usually in rural areas with little infrastructure and far from the grid. Many desire electricity to replace candles and oil lanterns with more convenient electric lighting, and to watch television and listen to radios without the continual need to replace or recharge batteries. The draw of the so-called modern industrial lifestyle is strong, and using electricity is one prominent characteristic of this lifestyle. The grid may never extend to all communities and homes. The capital is not presently available for such an expensive program. Where it does reach remote areas, the grid can be weak and unreliable. One way to provide electricity to areas poorly served by the grid is to use photovoltaics. The PV system can power a single rechargeable portable lantern, seen here at bottom left, or all the loads of a home. In either case, the electricity consumption tends to be very small, a few hundred watt-hours per day, so a correspondingly small photovoltaic system can be used. The PV system, unlike wind turbines or gensets, is simple, very reliable, and can be maintained by people who have no background in power systems. This is key in areas where there may be no local expertise to install or operate the system. The photo at the top left shows a batik used in Kenya to help communicate basic information about what photovoltaics are and what they can provide. To its right are two photos of solar home systems, the top one from Tibet and the bottom one from Swaziland. Note that they use only one module for each home. The fourth photograph shows housing for staff at a medical clinic in Botswana. With a solar water heater and a photovoltaic system providing electricity, the home has some of the conveniences of the city, making it easier to attract trained medical personnel to this rural area.
Remote cottages and homes. Examples from Finland and Canada. In some developed countries, many city people spend their summer at a cottage in the countryside. Some people flee the city entirely and choose to live year-round in an out-of-the-way home. The grid does not serve many of these cottages and remote homes, and photovoltaics have been very widely used to power their loads. PV's modularity permits the owners to start with a small system and add capacity over the years in response to changing loads or availability of funds. It is a simple technology that cottage goers and homeowners can operate, maintain, and even install themselves. And having fled from the city, these people are pleased by the absence of genset noise and ugly power lines. Cottages, which tend to be used predominantly in the summer, have good seasonal solar load correlation. Homes occupied year-round will often employ a hybrid system. In the photo on the top left, 2 modules mounted on the porch roof are sufficient to power the loads in this Finnish cottage. Each of Norway, Finland, and Sweden has tens of thousands of cottages with photovoltaic systems. The photo on the right shows a park warden's residence on the western coast of British Columbia, Canada. The wardens, whose mandate is to preserve the environment and provide a natural environment free of noise and visual pollution, are very enthusiastic about PV. In the photo at bottom, we see a remote home in Yukon Territory, Canada. The home, occupied year-round, has a large array as part of its hybrid system. Hybrid village power systems, examples from Morocco and Brazil. A previous slide showed how photovoltaics could provide power for lighting in individual homes in the developing world. Another approach to electrifying remote rural areas is to build a mini-grid for the village and use a photovoltaic hybrid system to power this grid. This has several advantages. It makes electricity available to a larger group of people, and it permits generation and storage capacity to be used more efficiently. Extending the grid to remote villages is often prohibitively costly. Transporting fuel to the site for a genset may be very expensive and fraught with the dangers of fuel spills and contamination. Using a photovoltaic genset hybrid system requires less fuel to be transported to the village. Usually such a system will also contain a battery. Human aspects are a key part of the planning and execution of these projects. It is essential that the system's users have realistic expectations about what the system can provide. They must understand that it does not offer the virtually limitless electricity of the grid, and that high-power loads such as irons and electric heaters will consume all the electricity that the system can furnish, and then some. They must recognize the consequences of adding new loads that were never envisioned during the design of the system. They must be informed that repeatedly emptying the battery of charge without letting it recharge will have detrimental effects on its lifetime, so that they can practice restraint. When realistic expectations are implanted prior to the installation of the system, people will be satisfied with its performance. The system must also include some mechanism to ration the electricity among the different system users, so that one user does not consume all, leaving the others with nothing. Such a mechanism should encourage use at times when the battery is full and the sunshine is strong, and discourage use when there is little energy available. Some people advocate imposing absolute limits on each subscriber's use of capacity and energy. Whatever the system, it should include safeguards to prevent theft of the electricity by unmetered loads. The social impacts of the system must not be neglected. Negative impacts may include the imposition of a heavy debt load and an exaggeration of the differences between rich and poor in the same neighborhood. Positive impacts may include greater satisfaction with living conditions in remote areas, thus stemming the tide of migration to large cities and making it easier to attract educated city people to work in healthcare or education. Finding the most equitable and reasonable way to finance and pay for the system is often a more complicated and important exercise than the design of the system itself. The photo on the left of this slide shows the students of a rural college in Morocco standing in front of the array of their hybrid power system. The photo on the right shows the array of a power system for an isolated village in the Amazon of Brazil. Industrial systems for telecommunications and monitoring. Examples from Antarctica and Canada. Photovoltaics power thousands of off-grid industrial loads the world over. PV's high reliability makes it ideally suited to critical loads such as telecommunications equipment and monitoring systems. Many of these loads are very remote. In the top photo, we see a hybrid system in Antarctica, thousands of kilometers from the nearest grid, powering a seismic monitoring station. At such remote locations, the cost of transporting fuel to the site may be several times the purchase price of the fuel itself. When there is a problem or maintenance is required, expensive trained personnel may need to be flown to the site by helicopter. This makes photovoltaics, which reduce fuel and maintenance requirements, very attractive. In general, the characteristics of gensets are the opposite of those of photovoltaics, and this makes them complementary power sources. Gensets have low capital costs but high operation and maintenance costs. By combining the two in the same system, a smaller PV array can be used, curbing capital costs, at the same time that fuel consumption is decreased, lightening the burden of O&M. An industrial application need not be thousands of kilometers from the grid for photovoltaics to make sense. The bottom photo shows a PV system powering the monitoring, control, and telecommunications equipment at a natural gas wellhead in Alberta, Canada. There are thousands of these systems in this area, and many are located right next to power lines. A PV system avoids the cost of the transformer required for grid hookup, is more reliable than the grid, which would require an uninterruptible power supply, and can be relocated should the well be moved. The PV system is a standard package that meets the needs of the wellhead regardless of its distance from the grid. On-grid buildings with photovoltaics. Examples from Switzerland and Japan. On-grid photovoltaics are rarely cost-effective without subsidies. Still, there are thousands of photovoltaic systems installed on grid-served buildings. Let's examine why. For many installations, a subsidy is a secondary consideration. Rather, people make decisions based on the image that their PV system would project, the environmental benefits it brings, or the long-term reduction in prices that a market stimulus will have. PV, generating electricity of something as ethereal as sunshine, is a space-age technology closely related to the semiconductors that animate our computers. To a company in, for example, Japan, photovoltaics may be a bold but sophisticated way to promote their high-tech, futuristic, and green image. Photovoltaics generate electricity without pollution, and their manufacturing process is quite clean. The energy used in their manufacture is generated 20 times over during their useful lifetime. People who feel a strong commitment to the environment may decide that minimizing their global impact is more important than having the least cost power source. For them, a PV system is a matter of principle. Governments recognize the long-term promise of photovoltaics to provide energy without pollution and greenhouse gas emissions. In order to encourage the research and development necessary to reduce costs in the future, some governments are willing to subsidize today's markets for photovoltaics. Such subsidy programs have been very successful in bringing down the cost of on-grid photovoltaics to a fraction of what it was only 20 years ago, and prices are continually being driven down. Utility, government, and manufacturer subsidy programs have worked best when they have made a long-term commitment to the technology. This gives research and development enough time to have an impact and encourages investment in larger, more efficient manufacturing facilities. In the top photo of this slide, we see residential roofs in Switzerland that are covered in photovoltaic roofing material. In the bottom photo, an office building in Japan has photovoltaics slickly integrated into its glass curtain wall. Water pumping systems. Examples from India and the USA. Photovoltaic water pumping is often cost-effective off-grid. Especially in agricultural applications, the need for water often coincides with sunshine, such as hot periods or summertime. A reservoir can store water for cloudy periods or nighttime use and is more reliable and robust than a battery. Water pumping can lead to major improvements in water quality. For example, a livestock watering system that obviates the need for the cows to enter into a slough to drink will reduce contamination of their water supply. This will be reflected in the better health of the livestock. For low-flow applications, the fuel saved by switching from a fossil fuel-powered pump to PV is not significant. But being able to put a PV pump in place and then having it run automatically is much more convenient than periodically transporting a fossil fuel-powered pump to the site. This is a major selling point for many farmers and ranchers. The reliability and simplicity of photovoltaics as a source of power for pumping is extremely important for water supplies to homes or developing world villages. It may be too expensive to bring trained personnel to these sites to operate and maintain more complex or failure-prone power systems. The photos on this slide show a livestock watering system in the USA and a village water supply in India, both powered by photovoltaics. The Indian arrays are mounted on a solar tracker which follows the position of the sun in the sky. The RETScreen photovoltaic project model. The RETScreen photovoltaic project model is a simple but very useful tool for a preliminary investigation of the technical and financial feasibility of a photovoltaic project. For an installation anywhere in the world, it can provide an analysis of the energy production, life cycle costs, and greenhouse gas emission reductions. The installation can be an on-grid system connected to a central or isolated grid, an off-grid system with or without a generator, or a water pumping system. To conduct this analysis, the user provides the site's monthly average temperature and monthly average daily solar radiation on a horizontal surface. The software includes a large database of solar radiation and temperature data from around the world. These monthly data are much easier to obtain and manipulate than the 8,760 values needed for an hour-by-hour simulation. While the RETScreen photovoltaic project model provides a lot of key information about the system, it does not calculate the loss of load probability, a measure of the system's reliability. It also does not model concentrator systems, which use reflective surfaces or a lens to boost the intensity of the sunlight falling on a photovoltaic device. The RETScreen PV energy calculation. The RETScreen PV energy calculation determines the performance of the PV system over the period of a year using monthly solar radiation and temperature data. Here we provide an overview of this calculation. For more information, see the RETScreen Engineering and Cases textbook available online and free of charge. The first step in the calculation is the conversion of the monthly radiation data for a horizontal surface into the monthly radiation data in the plane of the array. RETScreen's algorithms are able to perform this calculation for fixed or tracking arrays. The resulting data for radiation in the plane of the array are then used to determine the electrical energy produced by the array each month. For the on-grid model, the output of the array must be reduced by the losses in the inverter. For isolated grids, with much PV capacity compared to the loads on the grid, there may be times when the grid cannot use all the power provided by the PV system. The useful output of the array has to be reduced to account for this. For off-grid systems, RETScreen must determine what portion of the array's output is used directly by the load and what portion is stored in the battery for later use. The latter portion suffers losses due to battery inefficiencies. For hybrid systems, RETScreen then calculates the demand that cannot be met by the photovoltaic array and must therefore be met by the genset. For water pumping systems, the efficiency of the motor and the pump is used to calculate the fraction of the array's energy that actually lifts water. This is then converted into a quantity of water pumped through the specified head. The outcome of these steps is a calculation of the energy actually delivered to the load. Example validation of the RETScreen PV project model. The RETScreen software has been validated in a number of ways. For example, RETScreen has been compared with the National Renewable Energy Laboratory's HOMER simulation tool, which uses hourly solar installation data. In particular, an off-grid PV battery genset system in Argentina was examined. The system powers a 500-watt AC load and consists of a 1 kilowatt array, a 60 kilowatt-hour battery, a 7.5 kilowatt genset, and a 1 kilowatt inverter. On an annual basis, the two tools agreed to within a few percent for their predictions of PV array energy production and genset fuel consumption. For all months considered individually, the two tools agreed to within about 10%. This suggests that RETScreen can be as accurate as hourly simulation and is sufficiently accurate for pre-feasibility purposes. Conclusions. Photovoltaics can feed electricity to the grid, power off-grid loads, or be used for water pumping. Solar energy is available everywhere on the planet, and photovoltaic systems are already being used in every climate imaginable. The capital costs of photovoltaic systems are high, but their operating and maintenance costs are very low. PV is typically cost-effective when grid power is not available, especially if the load is small. On-grid installations of photovoltaics are generally not yet cost-effective and are often subsidized. Existing on- and off-grid markets for photovoltaics have led to rapidly declining costs.
The RETScreen software calculates energy production using monthly solar radiation data, but achieves an accuracy comparable to simulations based on hourly data. RETScreen can significantly reduce the cost of conducting preliminary feasibility studies of photovoltaic projects. This is the end of the Photovoltaic Energy Project Analysis module in the RETScreen International Clean Energy Project Analysis course.